In simple linear regression, we handled nonlinear data by trying transformations. In multiple regression, a common way to deal with curvature is to add powers of your predictor variables. And this is going to be the subject of polynomial regression. We have an example of a diamond price data set. It contains information on the price, carat, color, clarity, and depth for 351 diamonds. Suppose we want to predict price from the carat weight of the diamond. So we've got a scatter plot here of price versus carat weight. And you can see that it looks like the price tends to increase as the carat weight increases. However, it looks like maybe the relationship would be better modeled by a curve rather than a straight line that we've been doing in the past. So we're going to introduce the quadratic regression model. And that is y equals beta naught plus beta 1x plus beta 2 times that x squared plus an error. So all we've done different is add our squared predictor and another term in the model. As usual, we have the typical regression assumptions that we need to check. Note that this is still considered a multiple linear regression model, even though we've got that x squared in there, since it follows the form mu of y equals beta naught plus beta 1 times x1 plus beta 2 times x2. In our model, x1 is x and x2 is x squared. So that's the quadratic model. It's linear because it's linear in the beta coefficients. So we fit this quadratic model, and I've put it on the scatter plot here, and it looks like it fits pretty well. We've got our output from our regression, and all I did was add a column in my data set where I squared the carat column. And I put carat in the model for my multiple regression and carat squared also in my model. Now, if you'll notice, the R squared looks pretty good. It's 0.926. And I ran a simple linear regression fitting a straight line. Previously, I didn't show you the data here, but the R squared would have been 0.863 with simple linear regression. So we've got an improvement by adding that quadratic term, or fitting the quadratic model. So our R squared of 0.926 means that 92.6% of the variability in diamond price is explained using carat weight in our quadratic regression. Also notice that the adjusted R squared is 0.925, which is very close to 0.926. So this would imply that both of these predictors are important. Notice that the quadratic and linear term are both highly significant. And I want you to remember that if your quadratic term is significant and your linear term is not, it is conventional to keep both of them in the model. So just like in ANOVA, if you had an interaction that was significant and a main effect that wasn't, we recommended that you keep your main effect in the model. We're going to do the same thing here. If higher order terms are significant, then the lower order terms should be kept in the model even if they show a significant p-value or not. So let's take a quick look at the assumption checks for our quadratic regression. We've got a residuals versus predicted plot and a QQ plot, both from a software program called Minitab. Now notice that the QQ plot on the bottom is the normal probability plot, just has the axes reversed from the ones that I normally show you. It still has the same interpretation for our purposes. If the errors are from a normal distribution, it's going to show a straight line, and if it shows a shape, they're probably not from a normal distribution. All right, so let's take a look at these plots. We can see from the residuals versus predicted plot that it looks like we've got a problem with the variability in the errors being non-constant. It looks like they get wider in the middle values and narrower at the ends. It also appears from the QQ plot that our errors do not have a normal distribution. We do have a large sample size, but however, since we have, two violations here, we should use caution to use this model when making inference, but it still gives us good information about the relationship between diamond prices and carat weight. Some notes about quadratic regression. If collinearity is a concern in the quadratic regression model, then you can fit the model with x as your linear predictor and x minus the sample mean of the x's squared as your quadratic term. Then your quadratic term has zero correlation with your linear term. It's just a little trick you can use. Sometimes it's beneficial to add additional polynomial terms like a cubed term. The quadratic regression model is a special case of what's called polynomial regression. For a single quantitative predictor, x, a polynomial regression model of degree k is y equals beta naught plus beta 1x plus beta 2x squared plus all the way up to beta k x to the k, plus an error, of course. Sometimes it's beneficial to combine the idea of adding powers of predictors and adding interaction terms. Quadratic terms can handle curvature, and interaction terms account for effects at particular combinations of predictors. There's something called the complete second-order model, which includes linear and quadratic terms for two quantitative predictors along with the interaction term, and it is pictured here on your screen. Y equals beta naught plus beta 1x1 plus beta 2x2 plus beta 3x1 squared plus beta 4x2 squared plus beta 5 times the interaction x1 times x2 plus an error. As with any other multiple regression model, though, make sure to guard against overfitting, checking your R against your R squared and other tricks. You'll have practice with this in your homework.